Have you ever stopped to think about how absurd it is to see a bullet train cutting through the air at over 300 kilometers per hour? That metal monster weighing hundreds of tons gliding on thin rails as if it were floating. And while all this is happening, while the machine accelerates fiercely, and the world outside becomes a blur of indistinguishable landscapes, there is immense friction occurring right there, underneath, where the steel wheels meet the steel rails. This violent and constant contact should, in theory, generate absurd heat, so much heat that you would expect to see sparks flying, metal melting, the rails deforming like hot butter, but none of that happens. Absolutely nothing. And that's bizarre when you really stop to analyze the physics involved in this operation, because we're talking about monumental forces, kinetic energy being converted into heat through friction, and yet the trains continue to function perfectly, trip after trip, day after day, without the rails turning into a pool of smoldering liquid metal. And if you think this is just luck, or that the engineers simply hope for the best, you're wrong. Okay, you're very wrong, because behind this apparent simplicity lies such sophisticated engineering, so carefully calculated and executed, that it would leave anyone with even a modicum of curiosity speechless upon discovering all the secrets that make it possible. And that's exactly what we're going to explore now. Because the truth is that there's a very specific reason why high-speed trains don't turn the tracks into rivers of molten steel. And that reason involves a fascinating combination of materials science, intelligent design, and a deep understanding of the laws of physics that most people never imagined existed. First, let's understand the real problem here. Because when you have a massive object moving at absurd speeds on a solid surface, the friction between these two things generates heat. This is basic. It's high school physics. But the scale here is completely different from what you're used to imagining. We're talking about a train that can easily weigh 400 tons or more, depending on the model and the number of carriages. And all this weight is concentrated in tiny points of contact between the wheels and the rails. These are surprisingly small contact areas when you consider the total weight being supported, and these wheels are spinning at very high speeds because the train is traveling at 300, 350, sometimes even more than 400 kilometers per hour in some of the most modern trains in the world, such as the Japanese Shinkansen or the French TGV. And all this speed, combined with all this weight, should theoretically create a situation where the heat generated by friction would be enough to start softening the metal, because steel, which is the material used in both the wheels and the rails, has a melting point around insert value here, 1,500 degrees Celsius, but it begins to lose its structural properties long before that, starting to soften and deform at much lower temperatures. So how on earth did the engineers manage to solve this seemingly impossible problem of keeping everything solid and functional when the conditions seem to conspire to turn everything into a molten mess? The answer begins with something that seems counterintuitive at first glance. The fact that the contact between the wheel and the rail isn't as simple as you might imagine. It's not as if the wheel is constantly scraping against the rail, creating maximum friction all the time. In fact, when a train is in constant, stable motion, the wheels are rolling, not sliding. This difference is absolutely crucial to understanding the whole situation, because when something rolls instead of sliding, the friction involved is completely different. This is what we call rolling friction versus sliding friction, and rolling friction is dramatically lower than sliding friction. We're talking about a difference of several orders of magnitude. This means that the amount of energy being converted into heat is much less than it would be if the wheels were simply dragging against the rails. But that's not all. Not by a long shot. Even with lower rolling friction, heat is still being generated. And at such high speeds, and with such heavy loads, this heat could still be problematic if there weren't other mechanisms at play. This is where the choice of materials becomes absolutely critical, because the engineers who designed these systems didn't choose steel randomly. They chose specific steel alloys that have very particular thermal properties. These alloys are designed to have high thermal conductivity, meaning that the heat generated at the point of contact doesn't remain concentrated there, doesn't accumulate in that tiny point, creating a superheated region that could deform. Instead, this heat dissipates rapidly through the metal, spreading over a much larger area, both through the wheel and through the rail, This rapid heat dissipation is fundamental because it means that the temperature at any specific point never gets high enough to start causing structural problems. It's as if the metal itself is acting as a cooling system, transporting the heat away from the critical point of contact and distributing it over such a large area that the overall temperature remains manageable. Furthermore, these special steel alloys also have mechanical properties that make them wear-resistant, because it's not just heat that's a problem. Constant physical wear could also eventually create problems, but these materials are so tough and resilient. They can withstand millions and millions of posses without deteriorating significantly. But there's more, much more, because if you look at the design of modern rails used on high-speed lines, you'll realize they aren't simply metal bars thrown on the ground. They are carefully engineered to maximize the contact area and distribute forces evenly. High-speed rails are typically heavier and wider than conventional rails, precisely to increase the contact area and reduce pressure at any specific point. Because pressure is force divided by area, so if you increase the area while keeping the force constant, the pressure decreases. And lower pressure means less deformation, less wear, and less heat generated at concentrated points. Furthermore, these rails are installed on an extremely stable and well-constructed base, usually using concrete instead of traditional wooden sleepers, because stability is crucial. Any movement or bending of the rail during the passage of the train would create additional forces and could increase friction and heat. So everything is designed to be as rigid and stable as possible, creating a virtually immobile platform on which the train can glide with minimal resistance. Now, if you think you've already understood everything, get ready, because there's an even more fascinating layer to this whole story, and it has to do with the design of high-speed train wheels themselves. Because these wheels aren't perfect cylinders, as you might imagine. They have a very subtle conical profile, a carefully calculated taper that serves an ingenious purpose. This conical design means that when the train is turning, the wheel on the outside of the curve automatically has a slightly larger effective diameter than the wheel on the inside. This allows the train to navigate the curve more smoothly, with less lateral friction, because the two wheels can travel slightly different distances without slipping. And slipping is the enemy here. It's when you have slipping that friction skyrockets and heat really starts to accumulate. So this conical design is an elegant solution to minimize slippage and, consequently, minimize heat generation. And this is just one example of how every detail of these systems has been thought out and optimized over decades of development and refinement. There's another factor that most people never consider, which is the fact that high-speed trains aren't constantly accelerating or braking sharply. Most of the journey happens at a constant cruising speed, and when you're maintaining a constant speed, the amount of energy that needs to be dissipated through friction is relatively small. Of course, there's air resistance that needs to be overcome, but that resistance is mainly handled by the train's aerodynamics and the power of the engines, not by the friction of the wheels on the rails. Rolling friction at constant speed is surprisingly low. That's why trains are so energy efficient compared to other means of transport. They simply don't waste much energy on friction once they're in motion. This also means that not as much heat is being generated as you might imagine during normal operation. The heat problem becomes more significant during braking, when you're deliberately trying to convert kinetic energy into heat to slow the train down. But that's where the braking systems come in, which are specifically designed to handle this. The braking systems of high-speed trains are engineering masterpieces in themselves, because you can't simply slam on conventional brakes on something moving at 350 kilometers per hour and expect it to work. The kinetic energy involved is absolutely monumental. We're talking about values in the hundreds of megajoules and all that. Energy needs to be dissipated somehow when the train needs to stop. If you tried to do this using only conventional friction brakes, you would have exactly the overheating problem we're discussing. The brakes would literally melt. So engineers developed much more sophisticated systems. Most high-speed trains use what we call regenerative braking as the main system, where the electric motors are reversed to function as generators, converting the kinetic energy of the movement back into electrical energy that can be returned to the grid or dissipated through This handles most of the deceleration without generating excessive heat on the tracks or wheels. Conventional mechanical brakes exist as a backup, and for the final stopping phase. But they only handle a fraction of the total energy. And even these mechanical brakes are designed with cooling systems and special materials that can withstand the temperatures involved. And here's something that will really blow your mind. There's even consideration given to ambient temperature and weather conditions in the design of these systems, because the rails expand and contract with temperature changes. On very hot days, if the rails didn't have adequate expansion gaps, they could literally bend out of place, creating what we call sun kink, which is when the rail deforms due to excessive thermal expansion. So, high-speed lines are built with expansion joints, or more commonly in modern systems, with continuously welded rails that are pretensioned to compensate for thermal variations. All of this is calculated to ensure that even on scorching hot or freezing cold days, the rails maintain their perfect geometry and the wheel-rail contact properties remain ideal. This shows how every aspect of the system, from fundamental physics to environmental conditions, has been considered and integrated into the final design. So, when you put all of that together, when you consider rolling friction instead of sliding, the special thermal properties of the steel alloys used, the intelligent design of the rails and wheels to maximize force distribution and minimize hotspots, the sophisticated braking systems that prevent overheating during deceleration, and all the other hundreds of engineering details we haven't even mentioned here, you begin to understand why high-speed trains don't melt the tracks. It's not magic. It's not luck. It's pure engineering. It's applied science at its highest level. It's the result of decades of research, development, testing, and refinement by some of the brightest minds on the planet. People who have dedicated their entire careers to solving exactly this kind of complex and multifaceted problem. And the fact that these systems work so well, so consistently, transporting millions of passengers every day in dozens of countries around the world, is spectacular proof of what humanity can achieve when it applies rigorous scientific knowledge combined with creativity and determination. The beauty of it all is that you, as a passenger, never need to think about any of this. You simply board the train, sit in your comfortable seat, and a few hours later, you're on the other side of the country. And throughout this journey, beneath you, thousands of physical and chemical processes are happening in perfect harmony. The wheels are spinning at dizzying speeds. Tons of metal are balancing on thin steel lines. Immense forces are being managed and controlled. Heat is being generated and dissipated. And everything works so perfectly that you don't even notice. You can't even imagine the absurd complexity of what's making that trip possible. And perhaps that's what makes this story even more incredible. The fact that something so complex can seem so simple when it's working the way it should. Now that you know all this, that you understand the principles behind this marvel of modern engineering, the next time you see a bullet train speeding by, you'll look at those tracks and know exactly why they aren't melting, and you'll appreciate the human ingenuity that made it possible. So tell me in the comments, did you imagine there was so much to it? There's science involved in this. Have you ever ridden a high-speed train and are now looking at the experience with different eyes? Leave your comment, subscribe to the channel because there's much more fascinating content coming, and don't forget to leave a like. And since you've made it this far and clearly have a curious mind that loves to discover how things really work, click on that video that's appearing on the screen now and continue this journey of discovering fascinating curiosities that will completely change the way you see the world around you.